Take any topological surface, no matter how warped, stretched, or twisted it might be. Mathematicians can categorize it completely using a very simple set of structural rules. We will solve this classification problem by working through the exact logic laid out in James Munkres' classic text, specifically sections 77 and 78. Look at this diagram. Pasting specific edges of a flat polygon together constructs 3D shapes. Glue opposite edges here to get a torus. Instead of physically folding paper, we track this algebraically. Assigning a letter and exponent to each edge creates a labeling scheme. These alphabetical sequences define the physical assembly of the 3D manifold from a simple 2D polygon. This table maps the classification theorem. Every compact surface is homeomorphic to a sphere, a connected sum of tori or projective planes. You only need two coordinates to categorize them. Is the surface orientable? And what is its genus or number of holes? To prove this list covers everything, we have to mathematically manipulate flat polygon representations without changing their underlying topological properties. Mastering the elementary operations for transforming these polygons provides the mathematical engine needed to reach the final proof. Looking at this excerpt from section 77, we have 4 valid operations we can apply to a labeling scheme: cutting, permuting, pasting, and relabeling. In figure 77.3, we slice the polygon along a diagonal and paste it back together along matching edges. This action is an algebraic substitution. The cut introduces a new edge, C. The paste absorbs old edges, condensing the scheme into an equivalent string. Try this yourself. If you draw a diagonal from vertex 1 to vertex 3 on this polygon, what do the two new resulting labeling schemes look like? Repeating this step-by-step process of cutting and pasting creates an algorithm. It guarantees that any polygon, no matter how complex, will eventually be forced into one of our standard theorem forms. Section 77 works perfectly if you already have a flat polygon. But if you start with an abstract, highly twisted surface, where does that initial flat shape come from? As shown in figure 78.1, we solve this with triangulation. We break the complex surface into curved triangles. We lay these disjoint triangles flat and paste them along matching edges, building the unified 2D space needed for a labeling scheme. Triangulation provides the essential bridge. It translates an abstract topological space into workable, flat geometry. There is a potential hurdle. In figure 78.2, when pasting triangles, they must not accidentally meet at just a single vertex. If a vertex pinched this way, its local neighborhood would be disconnected, failing the topological requirement of looking locally flat. Munkres addresses this in theorem 78.2. He proves that for a valid compact surface, valid triangulations cannot pinch. They will always unfold cleanly. Because we can rely on the vertices behaving, we are guaranteed to get a single unpinched polygonal region. This gives us full permission to use the algebraic operations we established earlier. This flowchart maps the complete mathematical pipeline. We take an abstract surface, break it into a triangulation, and unfold it into a flat polygon with a labeling scheme. By cutting and pasting, we mathematically simplify it into a sphere, torus, or projective plane. If you found this breakdown helpful, like and subscribe for more visual deep dives into standard mathematical texts. Topology provides a rigorous structural understanding of shape. The classification theorem proves definitively that every compact surface is strictly determined by its genus and its orientability.